Hi everyone. Due to emergency issue, I'm very sorry that I cannot present our work face to face. I'm Chang Cui from Chinese Academy of Science. I'm going to present our work multi-objective cloud worker selection in crowdsourced testing. This paper is a joint work with Song Wang, Xunjie Wang, Yuanzhe Hu, Xing Wang, and my supervisor, Professor Ming-Shu Li. This is the agenda of my talk. Well, let's begin with the background and motivation. In recent years, crowdsourced testing is an emerging trend in software testing. There are many successful crowdsourced testing platforms in industry such as Baidu, CrowdTest, UTest, Testboard, and so on. Why do we need crowdsourced testing? Crowdsourced testing brings many advantages to us. Firstly, it can largely save time and effort of software companies. Secondly, because of the Android fragmentation issue, Android apps should be tested in large number of mobile devices, which is challenging for traditional testing. Thirdly, with the crowdsourced testing, software companies could save cost and have a flexible test organization. Crowdsourced testing can help through these three challenges. Therefore, it's adopted by many software companies. Here is the overall procedure of the crowdsourced testing. A task publisher provides a test task for the crowdsourced testing, include the software and the test requirement. Then cloud workers could sign in and perform the task and are required to submit crowdsourced testing reports after finishing the task. Finally, the task publishers needs to further inspect the submitted reports and verify whether they are bugs or not. Based on the procedure, we can find that who would accomplish the test task is important and critical for the crowdsourced testing. Because of the huge number of crowd workers, when a new test task comes, it is difficult to decide who can carry out the test task and give a good test outcome. We have collected 42 test tasks from one of the largest crowdsourced testing platforms in China. Based on the data, we accomplish our research and experiments. The ultimate purpose of the crowd workers selection is to select as few workers as possible to detect as many bugs as possible. However, there is no ideal test criteria for this purpose, because the real bug detection information of the test task can only be available until the test task is finished. We leverage three alternative criteria for selecting workers. The coverage of test requirements assures all the test requirements should be tested by the workers with similar expertise. Thus, we need to maximize the coverage of the test requirement. The bug detection experience of the selected crowd workers assures more experienced workers should be perform the test task. Thus, we need to maximize the bug detection experience of the selected crowd workers. The cost of the selected crowd workers consider the limited budget of the specific test task. Thus, we need to minimize the cost. In summary, we want to maximize the coverage of the test requirement, maximize bug detection experience of the selected workers, and minimize the cost. In consequence, our aim is to simultaneously considering the above three criteria. The main contribution of our work is we propose a multi-objective crowd worker selection approach which maximizes the coverage of the test requirement, minimize the cost, and maximize the bug detection experience of the selected workers to the best of our knowledge. This is the first approach for the multi-objective crowd worker selection problem. We evaluate our approach on 42 test tasks involve 844 crowd workers and 3,984 test reports. The data is from one of the largest crowdsourced testing platforms in China. The results show that our approach could improve the best baseline on average 17% in bug detection rate. Then I will introduce the detailed methodology. Our key idea is to model three test criteria into multi-objective problem and leverage search-based method to solve multi-objective optimization. The typical search-based software engineering method contains three parts: representation, fitness function, computational search algorithm. First of all, multi-objective optimization problem seeks to simultaneously optimize multiple objective functions. It can be defined as to find a vector of variable x, which optimizes a vector of m objective functions. The multiple objective functions are optimized using Pareto optimality. Specific, a decision vector x1 will dominate a decision vector x2 if and only if their objective vectors satisfy array fx1 greater or equal to fx2 and there exists I satisfy fx1 greater to fx2. Let's formally define the multi-objective crowd worker selection problem. Given a set of candidate workers W and a vector of m objective functions fi, the problem is to find a subset of workers S that is the Pareto efficient set. This is the overview of our approach. Its name is multi-objective worker selection approach, MOS for short. First, I introduced the representation. We encode each worker as a binary or variable. If the worker is selected, the value is 1. Otherwise, the value is 0. The solution is a vector of binary variables, which includes all the candidate workers. The initial population is generated random. Secondly, we introduce the fitness functions. For coverage of the test requirement, we use the technical terms in one's historical test report to represent his expertise. The coverage of the test requirement is measured by the percentage of all terms in the test requirement covered by the expertise of the selected workers. For bug detection experience of the selected workers, the bug detection experience is measured as the total number of bugs the worker detected before. Since duplicate bugs detected by the different workers are useless to the overall test outcome, we use the number of the unique bugs. For cost, we suppose all the workers who participate in the test task are equally paid. The cost is measured as the total review of the selected workers. Thirdly, we employed a widely used illusionary algorithm, namely NSGA2. In most, the 3 objectives are handled on obstacle scales. To make most more clear, I describe it using a running example. Firstly, the workers' historical test reports and test requirements are proceed to extract the technical terms. Then for each test task, whether a technical terms of a test requirement is mentioned by a worker, is encoded into a binary vector. Second, the bug detection experience of a worker is extracted and encoded into a binary vector. Thirdly, the cost of selecting each worker is set to 1 and also encoded into a vector. Fourth, the above 3 binary vectors of a worker are merged into one vector. Finally, the vectors of the workers for specific test tasks are passed into NSGA2 through several iterative generation, selection, and evaluation of NSGA2. The non-dominating solutions are finally obtained. Then we come to the experience and experiments and the results. We evaluate our approach through 3 dimensions: effectiveness of most necessity of the objective and the quality of results. Our experiment is based on data from Baidu crowdsourced testing platform. We collected 42 test tasks, involved 844 crowd workers, and 3,984 test reports. To explore the performance of our proposed approach, we compare most with 3 typical baseline approach. Random simulates the current practice in the most crowdsourced testing platforms. Bug ranking ranks all the candidate workers according to the number of historical bias. AR ranking ranks all the candidate workers according to the task similarity. We define a bug detection rate to evaluate the performance. We use cross-validation to evaluate our approach. We first randomly select 70% test as training dataset, and the remaining ones as the test dataset to mitigate the randomness. The experiment is repeated 20 times. For the parameters in NSJ2 used in MOS, we use random initial population of size 200,000 max evaluation, single point crossover, and bit flip mutation. The running time for NSJ2 is 3000 ms on average for each test task, which is negligible. This figure demonstrates the BDR comparison of MOS with different baseline approach. MOS outperform random. Selecting 10% workers, the BDR improvement is 148%. Selecting 30 workers, the BDR improvement is 48%. The average improvement of the BDR is 58%. The MOS also outperform both bug ranking and error ranking. The average improvement of BDR for bug ranking is 17%, and for error ranking is 25%. The results show that MOS can significantly outperform the current practice in work selection as well as two commonly used ranking methods. Therefore, MOS is effective for crowd work selection. Research question 2 is about necessity of objectives. The objective of cost is indispensable, which cannot be removed. Hence, we compare the performance of MOS when removing either of the other two objectives. We can find that MOS outperform the two bi-objective approaches. The average improvement of BDR for bug plus cost is 9.7%. For the curve plus cost is 5.7%. The results show that all the three objectives, which are the coverage of the test requirement, bug detection, experience of the selected workers, and the cost, are necessary in MOS. Here is the detailed results in 42 test tasks. MOS achieved the best performance in the most of test tasks. Research question 3 is about quality of results. We adopt three commonly used quality indicators: contribution, helper value, generational distance, to measure the quality of the results. The value of three quality indicators show that the results of MOS achieve high quality. Then I will quickly conclude our work. In this paper, We propose modes for cloud work session, which maximize the coverage of the test requirement, minimize cost, maximize the bug detection experience of the selected workers. Furthermore, we evaluate modes on one of the Chinese largest crowdsourced testing platforms. Our data has 42 test tasks involve 844 cloud workers and 3,984 test reports. From the standpoint of effectiveness, necessity, quality, and the results are promising. Future work will include the improvement of modes. We will deploy modes online and employing more test criteria. That's all, staff. Thanks for your listening. Sorry again for absence for the conference. If you are interested in our work or have any questions or comments, please email us.